Hey Code Websters, welcome back to another video in our series to build a neural network. If you don't know where you are, click on the above pop-up and start your journey with building a Python-based neural network. Today, what we're going to be doing is we're going to develop our training part. All right, last week we actually developed the querying, so you can query our neural network, but we want this neural network to actually do some intelligent design-based things. Okay, so if you're wondering how this actually works, I've added a lot of descriptions a lot of links in the descriptions, and a pop-up for a relatively good video that I watched. So essentially, we'll be using this formula to alter each individual weight. Okay, right. So for the hidden weights to the outputs rates, what we have is this formula, and for the input to hidden weights, we have this formula. And remember, this is the change. So this is how we're going to change it. We're going to add this to our previous weights. Okay, so let me try to explain that a bit more in detail. In both cases, alpha is essentially the learning rate. Output errors is just essentially the error that we get, right? So it's the actual error. So it's whatever we wanted to get minus whatever we got after we queried it. The hidden errors, there's a link in the description explaining that, but the hidden errors is essentially the errors that come from the hidden section. Okay, it's a bit confusing, but it's called backpropagation, and you'll understand it through the link. Then we times it by the sigmoid pre-sigmoid outputs. Then we times it 1 minus sigmoid pre-sigmoid outputs in both cases. And finally, we multiply by the relative inputs, right? So for the input to hidden layer, the inputs are the actual inputs. For the hidden to output layer, the inputs are actually the hidden values that come in. And we transpose that matrix. This is all in matrix form. Our hidden errors that we're going to be using is defined as the transpose of the weight hidden outputs times the output errors. And that will actually give us the effective hidden errors that we have. Now, that's a bunch of explanation. You might be confused, but let me tell you the gist of it. What we're essentially going to do is we're going to run our system an arbitrary amount of times. Each run, we will plug in how we want our network should work. So we'll give it some values, and we tell it, hey, this is what the value we want. Our neural network will look at those values. It will use our formulas from before to change our weights slightly so we have a more correct answer. So we might get an error. Pretty sure we'll get an error. There's like 1 in a million chance though that you wouldn't get an error. And then that error changes after each run. We kind of reduce the error. That's what the change of weight here is doing. So essentially we run our whole thing a lot of times so our network keeps going towards what values we actually want, and it eventually is effective at predicting what values we want. All right, so let's actually place this in our Python system. So let's bring that up. So in our class neural network, what we're going to do is we want to keep this really generic so we don't have to keep writing stuff for our future videos. We're going to just actually create a training function. Let me write that out and explain how that actually works. Okay, so let me try to explain that in a bit more detail. So just like our query system, we get our inputs, right? We put that in the right formation we want. We get our targets, which are similar to the formation of the inputs, and the targets are the actual values we want. We get our hidden inputs, right? So the hidden inputs sounds a bit confusing, but essentially what it is, it's our values that we got before we put the sigmoid onto it. Okay, we get the outputs, hidden outputs, which is the real outputs because we acted the sigmoid onto our hidden inputs. We get our final inputs, which is similar to the hidden inputs, where it's the output before we actually put the activation function onto it. We get the final outputs, which is the sigmoid onto our final outputs. Finally, we get the output errors, which is essentially just the difference between what we wanted and what we actually got. So this is really just the query system all over again. But now what we want to do is we want to actually implement our formulas from before. Okay, so let's actually create our hidden errors. Okay, so what we have here is we get our weights for the hidden to output layers. We add that to what our change. So it's the learning rate. We do dot multiplication between the transpose of the hidden outputs and the actual values from before. And this follows the formula, as you can see. The hidden outputs, obviously, you can see are the inputs for our system, right? It might be a bit confusing, but the actual hidden outputs are the inputs to our hidden to output section. Okay, so now we actually do the weights for the input to hidden layer. So as you can see, it's pretty much the same as the previous one, but we've changed the actual errors. So it's the hidden errors instead of the output errors. And we said hidden outputs instead of the final outputs, and we're using inputs instead of the hidden inputs. Okay, so that's our training done, right? It's really kind of confusing because there's a little bit of code, but a lot of maths into it. Trust me, the links in the description help a lot. If you just want to actually use this, actually want to understand this, or just want to use this without understanding it, this works as well. It's kind of like a black box type of system. It works pretty well as well. Okay, so let's actually change that. I think that's an error. That should be targets list, right? So we're changing targets list. Okay, so now we actually want to create our brain, right? So this is what I call the neural network is a brain, and that's the beauty of it. It's not something we just putting values into and getting values out. Not hard coding it, it's thinking for itself in a way. So let's go create that. Okay, so now we've created our brain. It's got 15 hidden nodes. It's got 3 input nodes and 3 output nodes. It's got a 0.3 learning rate. Okay, so now let's go ahead and actually, we'll be using this function later. So let's go ahead and create that. We're using a rounding function. Okay, so you might be confused at what this does. Essentially, if we've got like, let's say we have a list 3, and we wanted to round each value in there to whatever closest values we get, this will actually round that. So this will give you, if I use round eyes, that will give me 1, 2, 2, right? So we need that for our outputs, because our outputs actually will give us a value of like 0.99 or something along lines like that. We just want to round it to the closest number it is. And I'll show you that soon. Next, we're going to create a mapping function, right? And this is just a simple print. I just like to do this into a function instead of actually writing it out. Finally, we want to just get a loop for our system, right? So we're just going to loop that through, and we're going to say, hey, let's get some inputs from the user, okay? Okay, so let me try to explain that a bit more in detail. So we get 3 inputs, X, Y, Z. We put that into our array. We then get our actual query. So we query it and say, hey, neural network, we've already trained you up here, right? So we've, actually we haven't trained it. That's the next thing we're gonna do. But essentially it's gonna be trained. And we're gonna say, hey, neural network, we've already trained you. What am I gonna get? And it's gonna beep, pop, bing, network has decided. And it's gonna get the first 2 values. It's going to round the outputs because you might have like 0.99 and just set it as 1. Reshape it because it's a numpy array and we just want it to look a bit better, and get the first 2 outputs as well. Because remember, we don't care about the 3rd output. We just want to get the not of the first 2 inputs. Now, before we actually run that, let's actually go train our data. So we're going to train this about, I say 1,000 times. Okay, so now as you can see, we've trained our data. It's really easy to write it out. It's this is why classes are actually the best. I'm not going to start on that. That's going to make me go like really crazy on how classes are one of the best things ever invented. But anyway, classes just allow us to do this. We can just train it. And as you can see, we get opposites each time. Let me just double check that. Yep. Okay, so now all we have to do is run our system. Now let's hope there's no errors, but you know, that's life. You can sometimes get errors. So let's see. Okay, so now we got to input 3 inputs. So let's go 1, 1, 1. Okay, so it said 1, 1 maps to 0, 0. That's good. Let's try the other one. 0, 0 maps to 1, 1. That's good. 1, 0, 0 should map to 0, 1. And then finally we try, I think we tried 1, 0, 1, 1, and 0, 0. So we get to try 0, 1. I think that should work. Okay, notice we've actually don't need to put anything in the third one, but we kind of take it for, we don't need it, but we still put it in there just to give it some flexibility. And you can actually see if we change this to 1 as we did before, because we used 0 before, do that, we still get the same thing, right? So what I'm going to actually show you is I'm going to show you what our outputs actually are. And I'm also going to show you the hard outputs to explain why we use round dice. Okay, so let's go ahead and run that. 3 inputs. Okay, so as you can see, so 1, 1 maps to 0, 0, as explained before. The actual outputs are 0, 0, 0, which makes sense. Even though we've done 1, 1, 1. So this actually knots the whole thing, which is, it chose that to do it itself. The actual values are 0 0.03, 0 0.03, 0 0.002, okay? So in essence, it's not giving you out 0, but it's giving a number close to 0. And we're just rounding it to be 0, okay? So it's giving a like really high probability that's close to 0. Now, if we tried the same value and tried 1, 1, 0, we should get another thing, right? So in fact, it said, hey, 1, 1, 0 gives you 0, 0, 0 again. Right, so it makes up its rule completely differently. Since we haven't told it to do something with the last variable, it does whatever it wants to do with it. All right, I'm saying it because, you know, I'm not going to pointlessly genderize it. But okay, yeah, so that's our network working all fine and dandy. Next week, we're actually going to use image analysis. Okay, we're going to use this to analyze some images. And you'll see the beauty of this. Right now, it can just gives us a basic logic gate, but in the future, we can actually use pixels, analyze those pixels, and then say, hey, what pixel, what drawing, if I put a drawing into this, what will I get out of it, right? So we train it with pre-done images, and then we put a drawing of our own handwriting in there and say, hey, what is this value? And it'll actually give us the correct value. It's really exciting. So that's what we're going to do next week. You should all be really proud of yourselves right now because we've actually created a neural network just using NumPy. And NumPy is just a bunch of maths, right? It just helps us write an array. We could have done this all in lists. Would have been a ton harder, but a ton more code. It'd kind of be useless. But we haven't used any big packages. We just used NumPy. We used some functions, Skippy for special, for sigmoid functions. But yeah, congratulations, everyone. This is the end of our neural network using logic gates. Next week, we're going to actually do images.